So let's summarize the video that you just watched on basis, span, and linear dependence and independence. So the first thing was to realize what the span is. So the span of a set of vectors, span of v1, v2 up to vn. So the span of the set of vectors is simply a way of naming all the vectors, all the possible vectors that can be formed by doing a linear combination of the individual vectors in the set. Okay, so for example, the vector v equals twice v1 plus 3v2 would be inside the span of vectors v1 and v2. So that's the concept of span. Next, you learned the very important concept about linear dependence and independence. So what was that? So I give you a set of vectors, v1, v2, v3, v4, v5. Yeah? So let's write it as a set, v1, v2, and let's say up to vn in general, n vectors. So they are linearly independent if and only if, and that's why I'm using this symbol, if and only if, this linear combination of these vectors is always different to 0. Always different to 0. Except for the trivial case when all of the coefficients of the linear combination are 0. Okay? Now, this set of vectors are linearly dependent if and only if there exists one solution in which you can do a linear combination of the vectors and get a result of 0, okay, without having all of the AIs to be equal to 0. So that's the definition. Then another important concept was to remember what is the dimension of the span of vectors. And the answer is that if they are linearly independent, then the dimension of the span when you have n vectors is equal to n. So the dimension of the span is equal to the number of vectors. For example, if you have two vectors that are linearly independent, v1 and v2, their span is a plane, and this plane has 2 dimensions. Yeah? However, if the vectors are linearly dependent, then in this case, the dimension of the span of all these vectors up to Vn is smaller than n. So the dimension is smaller than n when the vectors are linearly dependent. For example, if you have two vectors that are on a line, they are linearly dependent, and therefore the dimension of their span is not 2. In this case, it would be 1. Yeah. Okay. Next important concept that you had to learn was the concept of a basis. So what is a basis? So a set of vectors that we usually call using the letter E when it's a basis, E1, E2 up to En. So this set is a basis of a certain vector space V if and only if all these vectors are linearly independent and they span the space V. Which means that if the space is n-dimensional, you need n vectors in the basis, because the span must have the dimensions of the space. Okay? And what does this imply? This implies that for any vector in this basis, in this space, let's call this a vector V. Okay, it can be written as a column of different numbers, and these numbers are V1, V2, up to Vn. These are not what we normally call the coordinates of a vector. So we are used to doing Vx, Vy, and Vz when the basis is x hat, y hat, and z hat. But in general, you have a basis, E1, E2, E3, up to En, and therefore you have coordinates V1, V2, V3, up to Vn. And what this means is that, so this is expressed in a basis E1, E2, up to En. And this means that the vector V is actually a linear combination with coefficients Vi, which are the coordinates of the vector. So this would be V1, V2, Vn, yeah, those are the Vi's here, multiplied by the corresponding basis vector Ei. So when you add those up, you're doing a linear combination of the basis vectors, and that's how you end up with your vector V. So any vector V can be written as this sum. And the notation we use is the column vector. So clearly there is a lot of information in this video. And next, I'm going to show you a couple of examples.